Vireen Vodapalli has 9 years experience in the industry, with the last 7 years working on modelling and methodology development for physical IP at ARM. Thank you for your time for today, Vireen. If you'd like to start.
Thank you, Sarah. So, my topic of presentation is Cosim for functional equivalence checking. And the co-author, Divesh, is also the co-author for this presentation. He's my colleague at ARM. So as I'm from a modeling and methodology team at ARM. So we develop physical IPs for standard cell memories and IOs. So we quickly go to the agenda for this presentation. So we have seen a couple of issues, the model which we deliver to our customers, especially on the interface IP, and from that we derived few of the verification requirements, and we see that we can address these verification requirements using the existing tools, EDA solutions. And then we also internally identified Cosimulation as a solution for this verification requirement. And when we implemented the Cosimulation methodology, we found some issues, certain issues. We'll also see those. And then finally, the summary. So ARM as a physical IP provider, we deliver front-end and back-end views to our customers. So front-end view is like a Verilog model, which is used in a simulation purpose. Which mimics the circuit behavior, whereas the backend model is a SPICE actual circuitry. So how it works here in ARM is, we as a front-end modeling team, we get the requirements from the circuit team, the specification for a given IO cell from the circuit team. We implement the model in Verilog. So it so happened that when we delivered the Verilog model to our customers, there are a couple of issues which were caught at the customer end. Majorly the reasons were the requirements, the specification we got from the circuit team had some issues, and the other problem was the front-end model which we developed, and we also write the test bench ourselves. So if the specification understanding is wrong at our end, the issue would not be caught. So this led to the couple of issues at the customer end. So with these learnings, we have come up with the verification requirements. So our verification requirements was to see that the circuit, the Verilog model, and the specification, all the three are in line. So for that, we tried with existing EDA solutions like formal verification tools like Conformal, but that it had its own limitations. One of the major limitations was IOs are complex, because the one more point to tell before we further go into the slides is this presentation is specific to interface IOs only. So with that, so the tools which we tried was Conformal, where because the IO interface is complex analog circuitry, the tools could not abstract the IO netlist and could not do the functional equivalence checking between the SPICE and the Verilog. And how the Conformal tools works is they usually work on the traditional or conventional way of designing the circuitry. If there is a new shift in the circuitry or a new shift in the design or a topology, tool will not be able to understand. That's another limitation. And the third limitation was IOs are very analog in nature, and we cannot exactly replicate the block by block in Verilog model. But whereas the Conformal tool expects that way, that's another reason which we could not succeed with the formal verification tools. So internally, we identified the dynamic simulation. It's a co-simulation. Co-simulation is nothing but a mixed signal simulation. as the solution for this problem. So for that, we on this solution we worked with EDA partners to implement this methodology. So further, the more details on this co-simulation we will be seeing in the further slides. So before going into the methodology, we'll see what a interface I/O, a basic interface I/O looks like. So it has the core side and a pad side. So where the core side will interact with the core, and whereas the pad side will interact with the external world. So if you see the EN1, when you enable the EN1, the A value is seen on the pad, and when the EN1 is disabled, the pad is tri-stated. The pad being tri-state is one of the major feature of the IOs. The reason being, when the pad is tri-stated, because the pad usually connects to a bus externally, and the bus is driven by many other pads. So when the other pads wants to drive the bus, the given IO has to be, the other IOs has to be tri-stated. So that's the one reason we have the tri-state feature in the IO. And there is other mode we call a receiver mode. So wherein when enable 2 is 1, the pad value is seen on the Y, which is the core side, and when enable is 0, the Y value will be 0. So for the easy understanding purposes and for the future slide purposes, what we have done was we have classified these signal pins or the pins into 3 categories. One is the signal pin. The signal pin is all the pins which would affect the functionality of the cell. And there is other set of pins we call it electrical pins. These are the pins which we do not model in Verilog because they affect the functionality they do not affect the functionality directly, but they affect the timing or the electrical behavior of the cell. And then we have a floating pins. The floating pins are the pins which does not affect the cell at all, neither in SPICE nor in the Verilog. But they are there in the cell because the other IOs which are sitting in a given ring needs this pin, and for that reason this pin is there in this cell, and that is for abutment purpose. So with these 3 classification, with this basic IO interface, we'll see what is the co-simulation. Instead of the Verilog model, we read in the SPICE netlist. Instead of the Verilog simulator, we have the SPICE simulator here. So what happens is the Verilog test bench applies a digital input to the SPICE, which has to be converted to the analog, digital to analog. The simulation happens in the SPICE. The simulated output is then again converted from analog to digital side, analog to digital, and then the simulated output is then compared with expected output in the Verilog test bench. And the control, since there is a discipline change A to D or a D to A converter, we need a AMS control file which basically defines the interface between this Verilog and the SPICE. If you overall see the setup, it is like a Verilog on the top, which is a Verilog test bench. The stimulus is coming from the Verilog test bench. There's a SPICE simulation happens, and the simulated output is then compared in the Verilog test bench with the expected output. So we'll see. We'll see each of these in more details in the coming slides. So how the vector file is generated. So what we have is internally at the ARM, we have created an in-house tool. What it does is it takes the truth table for the given IO and it generates the exhaustive vectors with the inputs and the expected output. The Verilog test bench then reads this vector file and it drives all the signal, power, pad as well as the floating pins. The electrical pins are not driven. The reason is they are not modeled in the Verilog, and the Verilog test bench, which was used to verify the Verilog model, the same test bench is being used in the SPICE. So for that reason, we do not have the electrical pins driven through the Verilog test bench. The Verilog test bench checks for the output 0, 1, and high Z, and not for the X. We do not check for X. The reason is the X in the SPICE side could be of two reasons. One, the output could be VDD by 2, or the output is undeterministic, where it could have 1 or a 0. Since we could not differentiate between these two behaviors, but the same, or these two behaviors is modeled as X in the Verilog, we cannot do the X checking. And the test bench also does the strength checking. How it does is it drives the weak value from the core side to the pad side, and externally we drive a strong value, and see the strong value is seen on the pad. The Verilog, as I was saying in the initial in the beginning of this slide, that Verilog vectors, or the vectors we generate as exhaustive, is used in verifying the SPICE netlist here, which otherwise would not. This exhaustive verification, if you would like to create through the SPICE test bench, it is very difficult. So as I've explained previously, that electrical pins are not driven from the Verilog test bench, they are directly driven through the SPICE, because the Verilog test bench are not driving this electrical pin, they are driven through the SPICE test bench. And the floating pins, they are tied to X in the Verilog test bench, because if the specification comes out to be incorrect, where it says this, it's an electrical pin, but actually it is not an electrical pin. If we do not drive X in the Verilog, we will not be able to catch. That's a major reason we tie X in the Verilog test bench, the floating pins. And then how an analog AMS control file looks like. So it has three sections. One is the SPICE test bench, which contains the path to the SPICE model, and the electrical pins which are not driven through a Verilog test bench are tied here to a given value in the SPICE test bench. And then we have the SPICE analysis options, where we specify the type of analysis and type of the integration method you want to run. And then the third section is the AMSD block, which is the core block which controls the interface between the Verilog and the SPICE. So for that, first we say that the configuration, we say that cell IO, the cell name, and then we say that instead of Verilog model, you need to use the SPICE model here. Since the Verilog test bench, which is expected to use the Verilog model, is now replaced with the SPICE model, then mapping between the ports or the nets in the Verilog test bench and the SPICE model is done by name mapping, and then it could be name or a port position mapping, but we are saying that the mapping has to be done by the name mapping. And then we have an interface element which basically the D2A or A to D part, how the interface between the A to D and D2A happens. So the interface element usually have these options. Basically, what is the supply level of the cell? What is the ground? What is the VT high? What is the threshold high? What is the threshold low for logic low? And we also define the voltage value, which is for Vx, basically V sub by 2. These are the inputs these are the basic inputs which required by any co-simulation tool in order to define the A to D or a D to A interface definition. So this is the overall methodology we run here at ARM. So first we take the Verilog's test bench and Verilog model, and then we do the initial Verilog simulation. We see that if the Verilog simulation passes for that IO cell, then we take that Verilog test bench and Verilog model. Along with that, we also have the SPICE net. Now the Verilog model will be Verilog model will be replaced by the SPICE netlist, and we have AMS control file and a probe.tcl, which basically to probe the internal signals of the SPICE netlist, and then it generates the simulation. The AMS simulation will generate the simulation log file and as well as the interface information log file. So the one reason here we need a Verilog model when we do a SPICE co-simulation is when basically for the port mapping, the Verilog test bench and the SPICE netlist, the port mapping, there are two options as I was saying in the previous slide. One is by the name and one is by the position. When we are going with the name mapping, we need a Verilog model. That is the only reason we need a Verilog model in the co-simulation. This is how the co-simulation looks like. So we have, this is the input pin, which is going from the digital to the analog side. So you have a D in, which is digital in, and an analog out. So if you see the value digital is 0, whereas the analog side you see a real value here. And then we have an in out, which is like a pad. You have a D in, which is a bidirectional here. If you see the icon here, it's a bidirectional digital input and an analog output. Again, we see the pad values as the real value. Here, if you see the digital D in is a digital value, whereas the A out is a real value. And similarly, the output will be on from the analog to the digital side. So we have the analog in and the digital out. So this is the waveform which usually the co-simulation waveform looks like. So once we have implemented this methodology, so with the EDA vendors, we engage with the EDA vendors and we implemented this co-simulation methodology. And then we started seeing some of these issues. So the majorly it is a high Z detection. So as I was saying, we also check for the high Z, which is very critical for the IOs. So the tool was not able to convert the SPICE side Z into the digital side, SPICE side Z into the digital side. So we engage with EDA partners to resolve this issue. So we found the two approaches for this problem for the IZ detection on the electrical side. So one approach is current based approach, where we measure on the output port the current and see if it is above the given threshold, a particular threshold. And if it is above the particular threshold, it is considered as a digital binary value. If it is below that, we consider it as a high Z. But for the threshold, in order to determine that threshold value, it is technology dependent. So the user has to give that technology dependent value, threshold value, current value. So then we had another approach which we call a voltage based approach. On the same, so what the tool does, or what the approach here is, from the output node here the output node, tool tries to trace the path to the VDD as well as the VSS ground and sees if there is any non-conducting device. And if in both the ground, the path towards the ground and a VDD, if you find a non-conducting devices, then the node is high Z. Then how the tool determines if a given device is a non-conducting? It goes and checks the operating region of that device. If it is the triode or a saturation region, it is considered as on. Otherwise, it is considered as off. Since the threshold of voltage, the operating threshold for the given devices is embedded inside the device model, the user need not have to give the threshold input, voltage threshold value, VTH. So how this can be enabled at the tool side from the tools is there should be an option for a given port, like enable this high Z. So something like that, an option should be available at the net or a port level. So this is another issue we found. Usually IO interfaces have the ESD circuitry because it protects the core. So these these ISD is modeled using a Verilog A or a B source element, which is a complex behavioral model. So tools usually will not be able to understand this complex Verilog A or a B source elements, and by default they consider it as a always on. Because of this reason, the tool was not able to detect a high Z in some cases. So what, see, we worked with EDA vendors. Again, we asked them to provide a switch like non-conducting _ some circuit or some circuit name. So we give those ESD device subcircuit names. So that for those subcircuit, tool will consider it as off always. That way we were able to resolve this high Z detection issues for the ESD devices. But then came another issue wherein the ESD device model is inside the device MOS model itself. So again, for that, the user has to the co-simulation user has to go identify the subcircuit which is ESD device inside the device foundry model, and then specify that. Then we have another issues where usually we found across the tools was usually tools insert a resistance value when there is at the interface of D to A converter, and that resistance, what it does is it pulls high or pulls low, because of which when the DVD value here, if you see the DVD from the digital side, it is driven 0, but you see on the analog side it is 0.463, which is above the VT low. So because of the high resistance tool inserts, we landed into this problem. So what the other recommendation is, go and change this value to a smaller value so that you will not find these issues. As I was saying, the floating pins, we drive X in the Verilog test bench just for the reason that it's actually a floating pin, not a signal pin. If the tools, by default, what happens is each individual tools will have its own behavior where they convert Vx from the digital side to analog side, either a 0 or a 1, or it could be VDD by 2. Since we are not sure how the tools are, by default it is handling, we need to explicitly mention in the A to D or a D to A converter that Vx has to be VDD by 2. So these are all the issues which we have seen on the co-simulation. So in the summary is, with the co-simulation, we are now able to align the Verilog front-end model specification as well as the actual SPICE circuitry, or all the three are equivalent. We initially, when we implemented the methodology, we started seeing many of these high Z issues. But when we worked with EDA vendors and resolved all those issues, we have now deployed this methodology in our production, and we are able to deliver our product of high quality.